If you're a newcomer to this channel, you may be wondering what Gleem is. Well, Gleem is an internet troll who hangs around Flat Earth and Flat Earth debunking channels, making inflammatory posts in live chat and long, mostly incorrect posts in video comment sections. Gleem claims he is not a flat earther, but he spends most of his time defending flat earth claims. Gleem says that he wants to see evidence that disproves flat earth, but when presented with such evidence, he makes utterly absurd claims that the evidence, like the observation on screen right now, can be explained equally well by both a flat earth and a globe earth model. The manner in which he does this is quite bizarre. He pretends to be an intellectual by posting links to academic websites that he doesn't understand. He also tends to be rather abusive and somewhat rude. I'm only engaging with Gleem today because he did attempt to show that one of my Traprain Law observations could be possible on a flat Earth. Of course, his attempt was an abject failure and revealed that he is incapable of performing even simple mathematical operations. Unfortunately, my video detailing the shortcomings of this back-of-the-envelope drawing seems to have triggered him somewhat and has led to his spam factory of a brain going into overdrive in the comment sections of my videos. So today I'm going to look at a couple of those comments before consigning Gleem to the trash can marked best ignored. This is going to be a bit of a dumpster fire, so I may need a bit of help. Fortunately, BlueMarbleScience has lent me Gladys for the day. Hey, Gladys. Go and get everyone else. This dumpster fire is going to be real big. Good girl, Gladys. Okay, let's light this thing up. Hello and a very warm welcome to you. Apologies for the slightly long intro, but I felt I needed to set the scene just a little bit. So this is a comment by Gleem on one of my videos. It's not as long as many of his comments, but it does contain the usual academic reference. Gleem says, "Miles Davis, please show me where I have gone wrong here. It'll be an absolute pleasure, Gleem." He says, "I have used an online calculator done by San Diego State University," and there's the link, "and found the approximate temperatures based on standard atmosphere table of 1976 of each altitude based on this data." And he posts a link to that site. And here are the figures I put in. So these are figures for the observation that I showed in the introduction to this video, or part of it anyway. And he states the result, which is finally we find the apparent altitude of the target, which is one of the mountain peaks, which has minus 10.74 minutes of arc and minus 0.179 degrees of arc. Then further down, he's still quoting the website results. In your case, the dip of the sea horizon is 26.04 minutes of arc or 0.434 degrees. These values place the target 15.3 minutes of arc or 0.255 degrees above the apparent sea horizon. the target is easily visible. This is now Gleem commenting, so why is this university website stating that you would have a sinking effect of 58.8%? You know, where over half of it would be missing due to the atmosphere. Now, please either correct me or explain why you omitted this, stating that this does not need to be even accounted for. You just need to look at that red dotted line for evidence. He says, I can feel Gleem Part 5 video coming on where you give me an apology. He wants me to give him an apology. He says, or shall I just ask everyone else? Question mark. Well, Gleem, it's going to be an absolute pleasure to show you where you've gone wrong, and I've got Gladys and her friends here to help me do it. Yes, Gladys, I know he won't listen, but I might as well do it anyway. So this is the University of San Diego webpage that Gleem used, which has the calculator on it down here where you can enter some figures. Now, I don't want this to become a long video, so I'm not going to go into massive detail about this calculator and this web page. If you want to know more, I suggest that you have a look at it yourself because it's quite interesting stuff. Let's just start at the introduction, where it begins. Sometimes we want to predict how high above or below the astronomical horizon a distant object such as a mountain will appear. This depends on both the curvature of the Earth and the curvature of the ray along which the light travels from the object to the eye. That's right, Gladys. It's a spherical Earth calculator. So just very quickly to remind you, this calculator uses spherical Earth geometry. States it at the very beginning, and there's a nice diagram here next to which it states the arc AB represents the surface of the Earth with the center at C. And the arc AB it's an arc, and it's placed on a circular surface of the Earth, two-dimensional representation of spherical Earth. And the geometry used and in the calculations and the algorithm is all based on spherical Earth, which is kind of important if you're trying to explain something in terms of a flat Earth Gleem. However, let's look at putting the figures in that Gleem used. So exactly the same figures as Gleem used as far as I can tell. I've got very, very slightly different result. I'm not sure why. We get an apparent altitude to the target of minus 0.178 degrees of arc. I'm not going to focus on that at the moment because Gleem concentrated on this line here in the answer or the result, which is to say the dip of the sea horizon is 0.433 degrees. Gleem had 0.434 degrees. Very, very small discrepancy there. And these values of arc place the target 0.256 degrees above the apparent sea horizon. Yes, Daisy, I'll tell him, don't worry. Now, Gleem has taken those figures and calculated in, I think, a completely incorrect way, a percentage. And he has then claimed that percentage represents some atmospheric refractive sinking effect. Yes, Rudy, I know. He's got that wrong as well. And it doesn't. But let's complete the calculations, something that I don't think Gleem did, or if he did do, he certainly didn't include it in his comment. So I used the same temperature figures and just changed the elevation and the distances for Ben Lomond and for Ben Narnain. I changed the temperature at the target for the Hopeton Monument because the Hopeton Monument is at the same altitude as the observer and only just over 8 kilometers away from the observer. And so the temperature at the Hopeton Monument should be the same as the temperature for the observer, and so I used the same temperature. This gave me the following figures. So my figures are in this first column, B here, and I have 0.256 degrees for Benim, 0.231 degrees for Ben Narnain, 0.315 degrees for Ben Lomond, and 0.315 degrees for the Hopeton Monument. And these are degrees above the sea horizon, with a dip to the sea horizon being 0.433. For some reason, probably only known to Gleem himself, he has chosen to take the 0.255 figure, divide it by the 0.434 figure to come up with 0.5875. And on this basis has concluded that there is a 58.8% sinking of Benim due to the atmosphere. I'll come back to that calculation and just how wrong Gleem is a little bit later in this video. But for now, let's have a look at how the figures that I obtained for all 4 locations relate to the observation that I actually made. Do they agree with that observation, or are they in some way different to what was actually observed in reality? Remember, these are based on globe Earth geometry, and so they should agree very well with what I observed if the Earth is spherical. So let's look at the predictions from the calculator that Gleem used in terms of those angles and see how well they predict what we actually observed in the photograph. So the angle from the sea horizon, now I can't mark the sea horizon because I don't think it's a trivial thing to calculate exactly where it should be in this image. I might have that wrong, but I haven't got the time to work it out. But it doesn't matter. What I'm interested in, and what we should be interested in, is the predicted differences in these heights of the various peaks and the Hopeton Monument. So the angle obtained for Ben Lomond above the sea horizon was 0.315 degrees. So exactly the same as the Hopeton Monument, which means they should be at the same height in the image, in the field of view. And if we draw a line across the screen, like I did before, we can see that that is indeed the case. Ben Narnain had an angle of 0.231 degrees, therefore somewhat lower than Ben Lomond and the Hopeton Monument, and that is indeed what we see. And let's place a line across the screen to the top of the Ben Narnain. And then finally we have Benim at 0.256 degrees, so it should be somewhere intermediate between the two. There's a little bit of cloud on Benim, so I'm having to slightly guess exactly where Benim goes, but that looks pretty good to me. Now we can actually use the predictions from these angles and compare them with the actual observed distances between the lines. So we know the difference in angle between predicted angle between Ben Lomond and Ben Narnain corresponds to the distance between the blue line and the red line. Likewise, between Ben Lomond and Benim is between the red line and purple line, and the difference between Ben Narnain and Benim is the purple line and the blue line. And I know from the PowerPoint program the exact location of this line relative to the top of the slide. So I can calculate easily the difference in centimeters between the lines. And when you do that, you get the following result. I won't go through every step. The important figures are over here to the right. So the top set of figures show that the purple line should be 29.76% of the distance between the blue and red line going upwards, or 70.24% of the distance going from the red line down towards the blue line. And that looks pretty accurate to me. But in terms of the actual measurements, as shown with the bottom pair of figures, we see that the actual distance measured on the photograph is 31.4% going from blue up towards red, or 68.6% going down from red towards blue. Those figures, I think, they're very, very close to the figures calculated from the angles that the website came up with. So I'm pretty happy with that. Certainly well within bounds of experimental error. So we have a curvature calculator based on spherical Earth geometry, one that takes account of atmospheric conditions, that produces results that agree almost perfectly with my observation. I know, girls, it's great, isn't it? So let's have a look at how Gleem arrived at that figure of 58.8% that he claimed was due to atmospheric sinking, and is in fact due to nothing of the sort. I've put together a little diagram in PowerPoint that I hope will illustrate this, make it a little bit easier to understand, even for Gleem perhaps. So there is Traprain Law, and there is the Hopetoun Monument. And we'll put a line across the screen going straight ahead from Traprain Law. Now, this is not going directly over the top of the Hopetoun Monument, it's slightly above the Hopetoun Monument. And this is what is the astronomical horizon used by the website. They account for refraction, and I haven't done, but that doesn't matter. It's a diagram to illustrate the point. This is the angle to the sea horizon, and it's 0.433 degrees. And that's the angle calculated from the astronomical horizon down to the sea horizon. Put Ben-Em into shot now, and it's to scale relative to the other two triangles. And this is the line of sight across the top of the Hopetoun Monument, which, as I said when I first made the video, is angled slightly downwards. And the calculator agrees and gives a value of 0.315 degrees, so less than the 0.433 to the sea horizon. Next, we'll put in the line of sight to the top of Ben-Em. And the calculator calculates the angle between that line of sight and the sea horizon, 0.256 degrees. Now, what Gleem did was he took that number, divided it by the 0.433, and claimed that this was 58.8% of the angle between the astronomical horizon and the sea horizon, and that was all due to atmospheric sinking. Of course, it's completely spurious to use that ratio at all, really, but what is it actually showing? What are the angles actually showing? Well, what the geometry here is showing, and this is the geometry used by the calculator, is that a portion of Ben-Em is below the sea horizon, and that the line of sight past the top of the Hopeton Monument to the top of Ben Eam has an angle of 0.256 degrees to the sea horizon. So that 58.8% that Gleem calculated is really nothing to do with atmospheric sinking. It's nothing to do with anything very much, in fact. It doesn't really relate to the portion of Ben Eam that is hidden below the sea horizon. It doesn't relate to the amount of gap between the top of Ben Eam and the line of sight past the Hopeton Monument. It is, as usual from Gleem, completely irrelevant. Yes, Dobbin, I agree. Maybe it's not his fault. Maybe he was dropped on his head when he was small. So, what can we say in conclusion about Gleem's rather overconfident, perhaps arrogant post? Well, firstly, he clearly doesn't understand what the web calculator is actually doing. Did he realize that it was based purely on globe geometry and therefore could say nothing about what would be expected on a flat Earth? I don't know. Maybe he did. Did he understand that the calculator, although it takes into account atmospheric conditions, the bulk of the angles that it produces are actually to do with the curvature of the Earth, and simply have an atmospheric refraction component built into those to perhaps give a more accurate answer than a calculator that doesn't incorporate any atmospheric refraction. And Gleem's claim that I've never accounted for atmospheric refraction is, of course, complete nonsense. I examined my original photographs using Walter Bislin's curvature calculator, which has refraction calculations built in and a sliding scale so that you can actually alter the amount of refraction present in the model. So Gleem, no, you're not getting an apology from me, but I haven't quite finished with you yet. Recently, in the last day or two, you've been posting some more comments. In fact, you seem to have been posting a huge number of very long comments. And let's have a look at one of them. So this is one of Gleem's more recent comments, posted 20 hours ago at the time I'm recording this. This is another typical Gleem post. It's got lots of academic sources referenced in it, most of which I don't think Gleem understands given past experience. And here he says, I have never said I fully explained it, meaning my observation in terms of a flat Earth. What I have said is that there are multiple factors which you have not accounted for. However, I can easily explain how this works on a flat Earth if you allow me to use the same nonsense information gathering you used. This is atmospheric sinking and a product of perspective. There, it's that simple. Well, I'm sorry, Gleem, it isn't that simple. My observation eliminates any problems with perspective whatsoever. That's why I chose to have the camera at 221 meters and look past the Hopeton Monument at 210 meters. Perspective means that the mountains will be smaller in angular size because they're a long way away, but they cannot go below the line at the top of the Hopeton Monument. And as we've just seen, atmospheric sinking is not what you have calculated or what the calculator there has particularly calculated, but we can have a look at what that website actually says about atmospheric sinking. So the same San Diego State University website actually has some quite interesting information and diagrams about looming, towering, stooping and sinking. And the section on looming and sinking show that actually they're the result of similar kinds of atmospheric refraction. But the section on sinking is particularly revealing, because it states that to produce sinking instead of looming, we need a model atmosphere with a steeper lapse rate than normal. However, there isn't much room to play with. The standard atmosphere already has a lapse rate of 6.5 degrees per kilometre, but convection limits lapse rates in the free atmosphere to about 10 degrees per kilometre. So I've used a model with that lapse rate. So they're using the model with the maximum lapse rate that you can have in free atmosphere. And the result is what you see at the left. You'll need to blink it against the reference case to notice the slight difference. So they're referring to this triangular shape, which is used in all their demonstrations, and this is the maximum sinking, and they say that in order to see any difference between that and this, which is the standard atmosphere reference case, you need to do a blink test because they look virtually identical, and I think you'll agree that that is true. They look identical. The case of looming, you get a big difference, and then there are other effects such as towering and stooping that also show significant effects. So sinking Gleem is not going to explain how those hills end up being so much lower down in the picture than they should be on a flat Earth. So I think that'll do for this video for today. I'll wind up by showing you once again the observation that I made from Traprain Law in East Lothian in Scotland. There are 3 mountains in this picture, and they should all appear way above that red line if the Earth is flat. Not just the peaks of the mountains that we're looking at the moment, but all of the mountain from its peak just about down to sea level should be above that red line, and it's not. Gleem has tried to claim that perspective and sinking, atmospheric sinking, can explain this. They can't. The rules of perspective and angular size and geometry dictate that the red line is a barrier that those mountains cannot cross. The only way they can cross that line, that barrier, if you like, on a flat Earth, is if there is some atmospheric condition that causes light to behave in a completely unknown way. So you have to rewrite the laws of physics in order to get this observation to work on a flat Earth. The challenge remains, and I'm open to being shown that I'm wrong. If someone can produce an explanation for this observation on a flat Earth, I'm all ears. But please don't do what Gleem's done. Don't just vomit a load of websites you don't understand and spout a load of text that makes very, very little sense and think that you have somehow achieved the goal. With that, I'll say goodbye and thanks for watching. And Gladys and friends, come on, let's go.